Okay. Okay, so we can start. Welcome to our afternoon keynote talk by Professor Leeat Yariv. Leeat is the Reinhardt Professor of Economics at Princeton University. She is also the founder and director of the Princeton Experimental Laboratory for the Social Sciences. So it's a great pleasure, Leeat, to have you here with us. She is the lead editor of the American Economic Journal Microeconomics, and she has served on the editorial boards of multiple journals. Professor Yariv's work focuses on political economy, market design, and social networks. She employs theory, laboratory experiments, and field studies to understand how individuals connect to one another and how they make decisions on their own and collectively. Today, she will speak to us about the effects of disentangling exploration from exploitation in bandit problems. According to conference rules, if you have any questions, please send them to me in a private chat message throughout the presentation, and I will ask our keynote speaker at the end of her talk. And the talk will last for 40 minutes plus 5 minutes for questions. Leeat, thank you again for accepting this invitation. The floor is yours.
Thank you. So I'll share my screen. Thank you very much for this introduction, and it's really wonderful to be here. And so I'm gonna tell you, like Dimitrios said, about disentangling exploration from exploitation, which is a project with my friends Alessandro Lizzeri and Eran Shmaya. So as a starting point, experimentation models are prevalent in our literature, and the reason is that many decisions are preceded by experimentation. Now, Dimitrios just alluded to the fact that I like lab experiments. That's not what I'm referring to today. So what I mean here is that you have some process by which you try things out before making decisions or search for information. Now, there's a vast literature in economics and computer science and political science, then medicine, that thinks about experimentation through what we call bandits. So just to give you kind of a background for this problem, the original bandit problem comes from a narrative that has to do with casinos. So you have a bunch of one-armed bandits or slot machines, and the basic ingredients of the model is that you need to try each of these machines in order to learn something about its distribution of returns. So in other words, the basic ingredients are that you have a bunch of projects. Here it's the slot machines with uncertain returns, and each period you can sample one project, namely pull the arm of one slot machine, and the reward that you get that period is intertwined with the information that you learn about that slot machine. Now, there are a ton of applications of this model. So it was perhaps first brought up in writing by Thompson in 1933, who thought about clinical trials where you try a new drug. And the problem is that you want to try it on a large sample of patients, but then your payoffs, good or bad, are intertwined with the precision of the signal that you'll get about the new drug. But they've also been used over the years for thinking about monopoly pricing, where the only way to learn about demand is to actually post a price, labor market choices, where once you hire an employee, you actually learn about them. You also get their production, political reforms that need to be tried out in order to learn about them, venture capital, where you need to put in money in a new company in order to learn the promise of that company, and team experimentation. And I'll touch on these particular papers in more detail soon. All right, so what underlies this problem is what's often referred to as the exploration-exploitation dilemma. So here, signals and payoffs are intertwined by assumption. And so what you do is you trade off learning or exploration and payoffs from exploitation. So in principle, if you think about those slot machines, you might want to just pull the arm of the most promising slot machine right now, but that might not give you the most information that you might want to get if you think about the future. So that's the exploration exploitation trade-off. This was considered a very difficult problem for many years. And in fact, Peter Whittle, who has been a major player on the math side of these problems and kind of a paper that describes his memories from the period in which it was conceived, mentioned in 1979 that the problem is a classic one. It was formulated during the war, and efforts to solve it so sapped the energies and minds of Allied analysts that the suggestion was made that the problem is dropped over Germany as the ultimate instrument of intellectual sabotage. Now, thankfully, John Gittins in 1979 actually came up with a solution. And what he suggested was that the solution is to actually have sort of a score for each potential project or each potential slot machine in the casino example. And every time you try a project, you adjust its score. And what you do at each point in time is just pick the project with the highest score. Now, this is a remarkable result, and the reason why it's remarkable is because the score that gets adjusted at every period is effectively separable across the project. So it doesn't matter what you see in one project for the score of another one. So that kind of gives you a very simple prescription. Now, calculating precisely the analytical form of the score is a complicated thing, but in general, it gives us a very simple structure for the solution. Now, the implications of the solutions are that you may exploit myopically inferior projects in order to learn. That's kind of the basic trade-off that you're facing. So sometimes you might choose a project that's inferior just in order to learn. You might switch between projects many times as you progress in this problem. And in the long run, you might actually get stuck on an inferior project. So that's a possibility. It happens with positive probability in many settings. Okay, so what I'm gonna tell you about in this project is a setting where the agents can actually separate the exploration from the exploitation. And we think this is important for a variety of applications, but just to give you some examples, you might think about exploring new policies while still implementing old ones. You might invest in one project, say a stock, while exploring others, researching other stocks. Even on-the-job search has some of these features where you're still getting payoffs from your current job, but you're exploring your future in other jobs that you don't hold right now. So our goal is to understand the implications on both the optimal strategies and the long-run outcomes. Okay, so just to kind of foreshadow what I'll show you, we're gonna focus on two Poisson bandits, and I'll show you the model in more details in a couple of slides. As it turns out, in this setting, when exploration and exploitation are disentangled, Gittin's beautiful result no longer holds. So I won't explain today, unless people ask me at the end, why that is the case. But as it turns out, there's no index. So we need new tools. But luckily, this problem is actually highly tractable. So what I'll try to show you is that there's always long-run efficiency with any level of disentanglement. The optimal policy here entails a lot of persistence relative to the standard model. And we see improved expected discounted payoffs, which shouldn't be a great surprise because we're giving our decision maker more freedom. But that improvement in expected payoffs is particularly pronounced for intermediate discount rates and priors. Okay, now I don't have a lot of time, so I'm not going to describe in great detail the related literature, but let me just give you kind of a glimpse of what strands of literature this speaks to. So first of all, there is a very large literature on Poisson bandits, and I already mentioned a bunch of applications that use the Poisson bandit framework, but Robbins was perhaps the first to actually write it down. Gittins suggested a general solution, and then Keller, Roddy, and Cripps, and Keller and Roddy actually actually brought to fame the Poisson version of bandit problems that I'll tell you about today. And I'll give you more details on what they did. Now, recently, there's been some work on the collection or choice of information sources. This is particularly relevant if you think about kind of media sources that compete with one another. So in some sense, you can think about the exploration in our study as a choice of what information source you're looking at as you get paid. There is also a sense in which our study relates to the rational and attention literature, because for us in the exploration decision, you decide which project to explore. And in some sense, it's just like allocating attention between projects. Now, the rational and attention literature took more of an information acquisition perspective on attention, but the two are kind of on a high level related. And the last strand of literature that relates to what we're doing is a literature from computer science that thinks algorithmically about good methods for solving these sorts of problems. Okay, so here's what I'll do to you in the next 30 minutes or so. So I'll describe the model in detail, and then I'll tell you about a special case that will seem awfully simple, but actually captures most of the applications that we've seen in economics of these problems with one safe project. Then I'll tell you what happens when there are multiple risky projects, and that will be it. All right, so here's the model. So the agent has to select one of two projects, L for low and H for high, in continuous time. Project X can each be good or bad, and whether project L or project H are good or bad is determined independently. So each project, be it L or H, is good with the corresponding probability P, and it's bad with the complementary probability 1 minus P. So again, this is independent across the two projects. Now, if project X is good, it pays a floor reward of R sub X, and if it's bad, it pays 0 forever. So why do I use the notation of L and H or low and high? Because conditional on the two projects being good, you always prefer the H or high project over the L or low project. Or in other words, the reward from a good high project is higher than the reward from a good low project. Okay, so what's the exploration part? At any moment, the agent has to choose what to explore and what to exploit. And we'll assume that exploration is free. So at each moment, the agent allocates a sort of a unit of budget. So here you can think about it as a unit of attention that they can split between exploring the high project or the low project. So if the agent spends a fraction alpha sub X of her budget exploring project X, she may receive some conclusive news. So if project X is good, she'll get the good news at a Poisson rate. That's why they're called Poisson bandits. And that Poisson rate will be proportional to the good news arrival that we denote by lambda, with a superscript of G for good news. If project X is bad, then she'll see bad news at a Poisson rate that's proportional to the arrival of bad news, which we denote with a superscript of B for bad. So there's an arrival rate of good news and arrival rate of bad news. Now, let me just tie it to what we already have in the literature. So special cases of the setting have been explored heavily in our literature. And what's often referred to as the classic good news case was suggested by Keller, Roddy, and Cripps in 2005. And that corresponds to a situation where the arrival rate of good news is always positive, and the arrival rate of bad news is precisely 0. Now, the classic bad news was introduced by Keller and Roddy, and that has the other polar extreme where the arrival rate of bad news is strictly positive and the arrival rate of good news is exactly 0. Now, to some extent, these labels are almost a misnomer, because in a way, the important distinguishing factor between these two cases is what happens when you see no news. So in the good news case, when you see no news, you actually become increasingly pessimistic. Whereas in the bad news case, when you observe no bad news, you become more optimistic. So the important aspect here is the information that's conveyed with no news, or what matters here really is the difference between the arrival rates of good news and bad news. Let me show it to you in a picture. So think about the case where the arrival rate of good news is higher than that of bad news. That's what we often refer to as the good news case. Now, if you think about the posterior that the project is good, when you saw no news as time goes by, you become increasingly pessimistic because you expect that if it's good, then at some point you should see good news. So as time goes by without any news, you become more pessimistic. So no news is bad news. And in the bad news case, it's the reverse. As time goes by, you haven't seen any bad news, you become more optimistic. So not seeing any news is good news. So as it turns out, you don't need to assume these extreme cases of zero on one of their arrival rates. Everything will go through even if they're positive. All right, so how about the exploitation? So at any moment, the agent chooses the project to exploit, and the ultimate payoff, which is unobserved, depends only on the exploitation choices. So the only thing that affects choices is the payoffs is the exploitation, and the payoffs are discounted at a fixed rate R. Now, we'll want to map the standard model to our model. So we'll do this through the alpha constrained decision process. So whenever the agent exploits project X, she must allocate at least alpha to also exploring it. So just to give you a sense of why this maps the standard model with the fully disentangled model, well, if alpha equals to 1, it means that whenever you exploit project X, you also need to explore it with your full budget. So that's exactly the standard model. If alpha equals to 0, it means that whatever you exploit imposes no constraint whatsoever on your exploration. So that's the full disentanglement case. Okay. Now, the first thing to observe is that no matter what alpha is, if it's smaller than 1, the agent exploits the best project asymptotically. And the intuition here is that whenever you have something still to learn, you will. Exploration here is free. So if there's any useful information for you that might, with some probability, improve your payoffs, then you're going to pursue it. So it doesn't mean that you learn all the payoffs of all of the projects. It just means that you learn which is the best project with probability 1. So this is in stark contrast with what happens when there's full entanglement or alpha equals to 1, where generically you can get stuck on a suboptimal project. So here, in some sense, alpha equals to 1, the standard model, is a very knife-edge case for our setting. Now, nonetheless, I should say that it may take a very long time to learn, and our agent discounts. So kind of how does it translate to payoffs is still a question. And that's why this is not a terribly insightful proposition. And I'll soon show you some payoffs that result from this process. Okay, so I'll start with the 1 safe project, and hopefully I can show you something about the 2 safe projects, the 2 risky projects. So this is the case that's most heavily studied in our literature in some sense. It's widely used in applications, and it corresponds to the setting where the probability that the low project is good is exactly 1. So this means that project L or low is safe, but it generates lower rewards than a good project H, because recall that the high project, when it's good, actually generates higher payoffs. So it still leaves you with an incentive to learn. Okay, so let's think about the general good news case. So suppose that the arrival rate of good news is greater than the arrival rate of bad news. So this means, again, that if you see no news, that's bad news. Now, in this case, exploration is trivial. You only have uncertainty about project H. So you should explore project H as much as possible. There's no point exploring project L. That's a safe project. Now, exploitation is less trivial because we have this constraint. So if you exploit project L, it actually limits how much you can explore project H. So that's where the analysis has to kind of kick in. All right, now when alpha equals to 0 and there is full disentanglement, then the problem again is very, very simple, because essentially now what you exploit doesn't affect what you explore. So you should just behave myopically. You should choose whatever project is the best one myopically. And in fact, if you just compare the expected payoff from pursuing project H when your posterior is PHT, then this is what you see on the left-hand side here. So there is this myopic threshold, which corresponds to the ratio of the rewards for the two projects that governs whether you exploit the high project or the low project. Now, when alpha is greater than 0, you may actually exploit the high project even when it is myopically suboptimal for information purposes. So the underlying trade-off is whether to exploit project L when it's myopically optimal and explore H at the rate of 1 minus alpha, or exploit and explore myopically the inferior project H in order to maximize the learning. Okay, so I'm gonna kind of show you some formulas, and that's just to convey some intuition. This will be the only place in this talk when I show you some formulas, so I hope you bear with me. So now suppose that you exploit the project L, you decide that this is what you want to do, and you explore H at the maximal possible rate, which is 1 minus alpha. If you think this is optimal, it better be the case that this is superior to a deviation that exploits H for a small duration delta and then switches back to L unless you see news. Right? Okay, so what would be the resulting equation for this? This is almost like writing a first order condition. So you have an immediate flow payoff difference because notice that L is here myopically optimal. So for a certain amount of time, you're actually going to get a positive payoff from sticking to exploiting L, but you would lose on information. So now let's look a little bit into this horrible monster that corresponds to the information term. How is it constructed? Well, you have the multiplier that corresponds to the discount rate. Then you have the probability that you actually learn that project H is good in this small interval delta that will cause you to switch. And you have the probability that if you didn't do this, you wouldn't actually learn in time. And if you have this extra information, you gain from the marginal benefit of using the high project. Now, why am I showing you all this? Because this is just copied, the same formula copied. The reason why I'm showing you this is because notice that this inequality does not depend on the rate of bad news arrival. It only depends on the good news arrival. So if we have the good news arrival rate coinciding with the bad news arrival rate, what we call both news case, we get exactly the same constraint. And this will be interesting for us later as well. Okay, so if we take the limit as delta goes to 0 and we simplify, we obtain a very simple cutoff rule. And in fact, when alpha equals to 1, we get exactly the standard threshold that Kelly, Roddy, and Cripps derived. So when alpha decreases, in other words, this constraint becomes more relaxed, this threshold increases and approaches the myopic threshold. There is less incentive to actually behave suboptimally from a myopic standpoint because there's less informational value in it. Okay, how about the bad news? So suppose now that the arrival rate of the bad news is the greater one. So no news is now good news. So now we could in principle do the same trick. So exploiting and exploring project H is optimal if it's better than exploiting L for a small duration of delta and then switching to H. So you could do the same sort of exercise that I just did, but what's important here is that the real value of information depends only on the arrival rate of bad news now. So in other words, the same sort of intuition that I just showed you for the good news case happens here. So the same sort of threshold that we'll get here should hold even when the arrival rates of good news and bad news coincide. In other words, we should get exactly the same formulation as we had in the good news case. So let me summarize this in a proposition. What governs here the ultimate cutoff for exploration is the maximum of the arrival rates of bad news and good news. And we have this formula that, that boils down to the standard formula when alpha equals to 1. And the cutoff satisfies the comparative statics you might expect that it would. So as we increase alpha, in other words, we make the constraint more binding, the threshold, the cutoff decreases. If we increase the rewards from information, we decrease the threshold as well. As we make the agent more impatient, they're less willing to choose something myopically suboptimal, and therefore this will actually be increasing. And when alpha is greater than 0, it's decreasing in lambda. So more arrival rate gives you more incentives to actually collect information and even use something that's suboptimal for a short amount of time. Okay, now we can also calculate the expected payoffs here. And so I'll just show you some pictures, but before I do that, let me just note the fact that when the agent is extremely patient, regardless of the constraint alpha, whether you look at even the standard model or the fully disentangled model, the agent is ultimately going to learn the optimal project and get paid very close to the optimum. So this is the case where the agent is extremely patient. So we shouldn't expect a very large difference from this entanglement. Now, if the agent is extremely impatient, regardless of alpha, whether you look at the fully disentangled or fully entangled problem, the agent essentially is going to behave myopically because they really care about their immediate payoffs. So again, we shouldn't expect a very high payoff difference. So now I'm going to show you pictures for this, looking at the extreme cases of alpha equals to 1 and alpha equals to 0. And I'll depict the expected payoff difference. And just so that we compare apples to apples, I'm going to normalize this difference by the full information expected payoff. So this is just because I'm going to change some of these parameters, I just want the comparison to be fair across the different figures. Okay, so here are the figures for the good news and the bad news. So you shouldn't be surprised that we see a positive difference. Disentanglement allows you more freedom and therefore increases payoffs almost by definition. What I want you to take out of this is, first of all, it's kind of interesting that there's a kink in the bad news case. I won't have time to talk about it, but they do look somewhat different. And second of all, you'll notice that they're maximized at intermediate values of parameters. So both in terms of the prior probability that the risky project is good, and in terms of the discount factor, which I just discussed. Okay, so the benefit is non-monotonic in both the discount rate and the arrival rate lambda. It's increasing in the relative rewards of the high to low project, and it's maximal for intermediate priors. In fact, you can show that it's maximized between the Gittins cutoff and the myopic cutoff. All right, so just to kind of summarize this one safe project case, we see that different projects are explored and exploited when you're less optimistic about project age. The optimal exploitation cutoff depends only on the maximum of the arrival rates of good news and bad news. And the payoff benefits of disentanglement are particularly pronounced for intermediate parameter values. And just to summarize it in a picture, this is what it looks for alpha equals to 0 and alpha equals to 1. So again, if we have here the probability that project H is good, there is a region here between the myopic cutoff and what we know from the Gittins index, the standard cutoff, that we might choose suboptimal actions for learning purposes. And you see that the alpha equals to 0 and alpha equals to 1 case lead to dramatically different behaviors. Okay, so this was the one risky project, and I'd like to tell you in the last 10 minutes about what happens when there are two risky projects. So suppose that both of the projects, the low and the high project, are both uncertain. So they both entail some risk. And now, just so that I can show you some intuitions, I'm going to first at least focus on the case of good news, where the arrival rate of good news is higher. And if I have a minute in the end, I'll show you the result for the bad news. It's similar, but not identical. All right, so let's first think about the standard setting. So this is the setting in which exploration and exploitation are fully entangled. So how does it work? Well, you start exploring and exploiting the project with the higher Gittins index. This is basically what Gittins told us to do. And then if you don't see any news, then you become increasingly pessimistic about this project. And in fact, the Gittins index is going to decline. So at some point, without any news, the Gittins indices of the two projects are going to coincide. Now, at that point, you're going to mix across the projects until you see news. So in our setting, you effectively can have infinite number of switches between the two projects. Now, whenever you see good news, the Gittins index jumps. And once you receive good news, there's no more learning on that project. So you continue forever with that project, even if it's the low project. And that's where you see the incomplete learning. So it might be that the high project is still good, but your Gittins index jumped up for the low project and you get stuck there. So what's important to take from this is that you might have infinite switches and incomplete learning. All right, so now let me show you what happens when you disentangle exploration from exploitation. And just so that we can describe things analytically, I'm going to assume that alpha equals to 0. So in other words, we'll think for simplicity just about the case of complete disentanglement. So now exploitation is trivial. So just like in the one safe arm case, if exploitation doesn't constrain your exploration at all, you may as well just exploit myopically the optimal project at any point in time. The exploration is a bit trickier, so that's where we need to characterize things. So now, just to kind of, before I describe to you the main result, if you observe good news on project X at any point in time, then if that project is the low project, we're basically back to the one safe project case, because at that point, the project L, you know it's good, so it's safe. And you have this risky project H, it's just like the case that I described to you before. If you learn that the high project is good, then the world is great at that day, and you exploit project H forever. There's no point, and you can explore project L if you'd like, but it's never going to change what you do. Now, if you observe bad news on project Y, then you should immediately switch to the other project and exploit that. If you receive news that the other project is also bad, then it's a very bad day, and it really doesn't matter what you do, you're going to get 0. Okay, so before I describe to you the main result, let me do a quick detour on just some terminology that I'll use. So first of all, we'll say that project X is active if it's the project that you exploit. So in other words, if it generates a higher expected payoff myopically than the other project. Now, if you explore an active project, then there's going to be a time at which if you see no news, you're going to hit exact indifference between the projects. So recall, we're in the good news case. Not observing any news makes you increasingly pessimistic. So at some point, you're going to hit the precise indifference. Well, let me show it to you in a picture. So suppose that project H is the active one, the high project, and you decide to explore it. So you start out by thinking this is the better project. It's more promising, it's higher, it has a higher expected utility. But as time goes by and you observe no news, you become more and more pessimistic until at some point you're precisely indifferent between the low project and the high project. Okay, so here's the proposition. So suppose that project X is active at the outset. The optimal exploration strategy entails exploring project X for some amount of time, which is lower than this time till indifference and potentially 0, or indefinitely until you see good news. And after that, you explore the other project until you see good news. So in other words, indefinitely, unless you see news. Now, furthermore, if you restrict attention to one of these extreme cases where the arrival rate of the bad news is actually 0, then we have very extreme solutions. So you're going to explore indefinitely one of the two projects. So this means that in this setting, you're going to switch exploration at most once, unless you observe news. And you're going to switch the exploited project at most twice. Now, these precise numbers are not terribly critical, but recall that in the standard setting, we saw that you would switch an infinite amount of times. So here it looks very different. Okay, let me give you a kind of a special case, and then I'll show you a very hand-waving brief intuition just to give you a sense of what happens here. So suppose that you have identical projects. So everything is completely the same. They have the same prior, the same rewards, the same arrival rates. Let's say that we have this extreme case of no bad news. So it's really the simplest case possible. And just to get a sense of why you stick to one project. Now, in the standard model, you're completely indifferent. So you're going to mix between the two projects equally until you get news. In other words, you're going to get a whole lot of mixing. Now, in our case, when there's full disentanglement, you're going to exploit one project and explore the other until you get news. Why is that? Because after an infinitesimal amount of time, no matter what you observe, you're going to be more optimistic about one project relative to the other. So one project is going to be myopically optimal. Now, if you divide your attention you're going to receive news that will tell you to switch from your project at only half the arrival rate. So what's critical here is that what you want, the value of information, comes from the fact that it will actually affect what you exploit. If information is just going to reinforce your choice already, it's completely useless. So you may as well look at the other project, which is the only information that might actually change what you do. Okay, so let me give you the hand-waving intuition. So assume that you start by exploring project Y. So after some time with no news, you exploit project X because you become increasingly pessimistic about Y. And then information is valuable only if it can lead you to switch from project X. Otherwise, you're already doing what is optimal, so it doesn't matter. Okay, so only good news on Y can cause an exploitation switch. So the optimal exploration at that point depends only on the arrival rate of good news on project Y, not on the arrival rate of bad news. So this is kind of similar to the intuition I showed you for the one safe project case. So in particular, we can assume that the rates of news arrival is exactly the same. It wouldn't change your optimal behavior, or what I call the both news case. But in both when both news arrive at the same rate, if you see no news, you learn nothing. The problem remains exactly the same. There's no bias towards good or bad. So in other words, if you started out by exploring project Y, you shouldn't change. Nothing has changed after a while that you've looked at project Y and saw no news. And that's basically what we see in this proposition. Now, I don't have time to tell you about the bad news and some of the comparative statics, but let me just highlight some of the possible applications before I finish. So we think this might be interesting in terms of team problem. And we know that in the standard model, there is a kind of a free riding problem that emerges when teams experiment together. In our setting, there's actually efficiency. We think this sort of model is very relevant for delegation problems. So you can think about one agent who explores, like an intelligence agency, and the other who exploits, or you can think of it as the executive. And if they have conflicting objectives, this becomes even more interesting. So in some sense, what I showed you today is a setting where there are fully aligned objectives. And we're also thinking about this as a model of on-the-job search and climbing the job ladder. This kind of requires more explanation. Okay, so just to conclude, I hope I convey to you that this is a fairly simple and tractable framework for disentangling exploration from exploitation. It covers many special cases that the literature has looked at. Disentanglement has substantial effects. The option to disentangle is utilized non-trivially. It affects persistence of the choice of projects to both explore and exploit. And it has serious payoff consequences that are particularly pronounced for intermediate parameters. And hopefully it's useful for a variety of applications. So that's all, folks.
Thank you so much, Leeat, for giving us this novel perspective on this very classic problem. And I have some questions, but let me just give first the opportunity to our audience, if they have any questions, to ask them. I don't see anything in my chat. So I will ask something. But just I mean, I'm not obviously an expert in this literature, but what I was thinking is the following. So what you're essentially doing is you're slicing attention. So you allow the person to slice the attention among projects, but you still maintain the constraint that they have to put exploration on one project. exploitation, exploitation on one project. And at least for the case of alpha equals 0, so for the full disentanglement, I think that the more general model may be that you could also split exploitation. That your solution might be also the solution to that model as well.
Yeah, it wouldn't matter. Yeah, because you would always, it's like a, standard best response, right? So you would always be best responding with the myopically optimal thing. So you might say when I'm indifferent between the two projects, I could split my exploitation, but then it wouldn't affect payoffs.
But would we have any idea what would happen when alpha was not equal to 0? So in a more general setting. So since now by your results, we can start from there, maybe, I don't know, maybe we could gain some insights there.
Yeah, so as it turns out, you never want to actually, not in a way that's meaningful for payoffs, you never want to actually split your exploitation. So we actually started out writing the model that way, but then we realized that it doesn't actually give us anything. So that's why we dropped it. But it's a good question. Even in the Keller-Roddy-Cripps setting, they actually allow for the split, but it never really has a bite.
Okay, good. So you can have a more general setting where you can split your attention and your exploitation decisions, and still for the exploitation part, we would derive to the standard model without slicing. Exactly. That's good to know. Okay. And something else that you mentioned by the end of your talk regarding Pandora's rule. So I guess that, okay, there are alternative search problems, like where exploration is in principle disentangled from exploitation. So you have to look first around and then to decide where to exploit. Do you find any connections now that you have disentangled them in the bandit problems that?
Yeah, so just for those who don't know, the Pandora box problem is a setting where you have a bunch of boxes and each one is associated with a reward and some probability of a reward. And once you open the box, you see immediately the reward, and then you can pick a box when you open them, and there are various variants of that. So yeah, we've been thinking about looking at that problem from our perspective as a way to think about climbing up the job ladder. So in some sense, every tier of your career corresponds to a bunch of Pandora boxes that have the same rewards and the same probabilities. So in some sense, you start out as a junior faculty and you maximize and you finally find a university that is a great fit for you. And then there's no reason for you to look at equivalent jobs for you, right? You don't explore at the same tier. What you might explore is Pandora boxes that are at the higher tier, where you might be hopeful that that would be a superior match for you. So we use this sort of setting to think about how you climb up the job ladder, but it's a somewhat different model, so I'm not sure.
Okay.
It's in the same umbrella.
Okay, great. Thank you very much again for this presentation of these new exciting results. And I don't know, we'll have a break for a few minutes and we'll continue with the remaining sessions. Thank you, Leeat. Thank you all. Bye-bye.